So now we're going to turn our attention to take a look at a very special case of a normal distribution into what we call the standard normal distribution. Now, to give us a little bit of a guide into this, let's take a look at what we have in the box up above. You might recall that earlier in this semester we talked about the idea that we could measure the position of a data point using its z-score. That is, we calculated how far away it was from average and divided by the number of standard deviations to get our z-score. Well, the interesting thing is that we can use that fact to help us calculate some probabilities. Now, this might seem weird at first, but we'll tie it together in the next section. But first, let's take a look at just how this would actually play out. First, we'll see that what we're going to be dealing with here is, again, what we call the standard normal distribution. This is going to be the normal distribution that has a mean of 0 and a standard deviation of 1. Whenever we have a normal distribution with these properties, we call it the standard normal. The reason for that is because the reason why at least it gets a special name is because we can start to see some very interesting things here. When I move out to a z-score of 1, that is, I move 1 standard deviation to the side, notice that the value on the x-axis that I'm staring at is the number 1. Notice that's not always the case with every normal distribution. If I was to draw an arbitrary normal distribution like what we had in the last video, I would have had mean of 45, standard deviation of 12. By going up 1 standard deviation, I could land at a totally brand new number never yet talked about, like a 57. But here, when I go up 1 standard deviation, I land at the number 1. So what's interesting is that the numbers that exist along the x-axis here are actually, or can actually, be thought of as z-scores. So oftentimes, in previous problems, we labeled our axis down here with x. However, in this distribution, we're going to label it with z because the numbers down here can represent z-scores. So when you hear standard normal distribution, you should automatically think z as our variable. So let me show you how this works. We're going to try to redo all of the questions that we did in example 2, but we're going to first calculate a z-score for the given value of x, and then use a standard normal distribution to help us calculate a probability. Let's take a look at what we mean by this and see what kind of interesting things emerge. I want to find the probability, again, back from example 2, that the shopper will be in the store for more than 39 minutes. Okay, I'm actually going to go ahead and draw 2 quick pictures here. So I have this picture. I'm going to set up another number line down here for my second picture. Now, in my first picture, I'm going to go ahead and sketch out my nice normal distribution, but I'm going to make this picture about x. So in the variable of x, that was the amount of time the shopper spent in the store, the average was 45 minutes, and the standard deviation for x was 12. And so we saw that when we wanted to go more than 39 minutes, we just went ahead and we drew a picture that looked like this, right? Now, in fact, you can even go back, take a look at what we did on example 2. We made a picture exactly like this. So we're not changing the problem at all. However, I'm going to create a second picture down here. It's going to look almost identical, except for a couple things. What I'm going to do is I'm going to replace all the numbers on the x-axis with their z-score. Well, 45 is a really easy z-score to calculate. You don't even need the formula for it, because you can ask, how many jumps or how many standard deviations away from average is 45? Well, it's not away from average at all. It is average. So its distance from average is 0. So how many jumps is it from average? 0. But notice if I want to calculate the z-score that goes with 39, which would be right here, to find that value, I'm going to actually have to go ahead and use my z-score formula to calculate this. I'll even write up here, the z-score for 39 is, well, let's see. Remember my formula up above would say 39 minus my average over my standard deviation. Well, let's see, 39 minus 45, that's negative 6. Divide by 12, that would be negative 0.5. Remember, it's okay to have z-scores that are negative. In fact, in this case, it makes a lot of sense that it would be negative because the number I'm looking for is below 0. So now I have this value, negative 0.5. So what I'm going to do is take a look at the following. I know that back in example 2a, when I calculated this probability, the total space there was 0.6915. Let me write that down up here. I again know that this amount of shaded space was 0.6915. What I'm curious about now is how much shaded space is right here. Well, let's calculate that. This would be the probability that z is greater than negative 0.5. Notice that's exactly what I've shaded. And since this is a normal distribution, it just happens to have a mean of 0, and the standard deviation for the z is 1, then I can go ahead and set up my normal CDF to help calculate this. So my blue space starts at negative 0.5. It stops, well, technically nowhere. It goes on forever, so we'll put in 1E99. The average for this picture that I'm working on is 0, and the standard deviation for that picture is 1. Well, I'm curious what number I get back when I actually attempt to crunch this out. Let's flip over to the calculator and see what we get. Okay, so on the calculator, I can click second, vars, go to normal CDF. I know that I want to go from a negative 0.5 up to a 1 E99, and then I want to do 0 for my average, 1 for my standard deviation. Remember, I'm picking all these numbers from the second picture. Now notice when I click this, I'm going to get a value back of 0.6915 if I round up to 4 places. So I'm going to write that down, 0.6915. So again, this number here is going to represent the amount of blue space that was sitting right over there. Do you notice something? Well, yeah. You probably noticed right away, wait, these things produced the exact same answer. They're identical answers. There's no difference between what I did in number 2, part A, and on number 3, part A, except that I guess on this part A I had to do a little bit more work because I had to find a z-score. So this may seem kind of strange. Why in the world do we care about this? And again, for the moment, I want you to save that question. It's a very good question, but I want you to save it for the next section. Right now, we just want to highlight the fact that we can, if for any reason we really wanted to, convert over to z-scores and then calculate our probabilities. And we know that we'll get the same exact probability. I'm going to ask you to go ahead and try to practice this with parts B and C, which are the same exact parts B and C that you had back in example number 2. It might even be helpful again to redraw the pictures from example 2 and think about how you're just going to find the z-score for each of the new blue numbers. Why don't you go ahead, give that a try, and of course you can check your solutions up online. The Blackboard notes are posted there, and that'll be a great spot to go back and review them. I won't go ahead and do these problems throughout this video. Keep in mind, though, again, this is just an option for how we can compute a probability. Most of the time, we will just compute our probabilities directly, like we did in example 2. It's less work. But we will see in the next section why this can be advantageous in very rare circumstances.